Hello, my name is Kostas Yalitakis. I work as the technical artist teacher here at the Game Assembly in Malmö, Sweden. And this video is part of the Getting Started with ShaderFX for Maya series of videos. This is part 2, and I intend to talk about basic shader math and just showing some of the more common nodes that I usually use. So these are the topics I'm going to be talking about, or the things I'm going to mention. The first one being that colors are represented as 0 to 1 values, what to expect when multiplying, when adding, and when subtracting, what is a 3D vector, and then just a list of common nodes that I want to go through that you'll frequently use, or likely. I tend to use these at least. So I'll start from the top and I'll go straight into Maya. So the first topic or point was that colors are represented as 0 to 1 values. If you work with colors in any other technical content like shaders or VFX or whatnot, you're probably aware of this already. But if you're used to, say, Photoshop or any other 2D painting program, you're usually used to defining colors with a 0 to 255 value. Those represent the 256 colors that you usually have, or that you have in an 8-bit image, 8-bit per channel actually. However, when these colors are actually calculated and used by the computer internally, probably nothing you need to worry about when you're sitting in Photoshop. They are handled as 0 to 1 values. What that means is, if we have a look at these example images I loaded, a black color is 0.0 and a white color is 1.0, and everything in between there sits in that range between 0 to 1. It makes it a lot easier when doing a lot of the math operations that you'll be doing if you get into working with shaders. So I've just, for the purpose of showing some of these basic math operations, I've loaded 6 different textures that we can play around with. And the 4 coming points that I wanted to just showcase some examples is what to expect when using the multiply operator and the addition add operator and the subtract operator. So these are just texture map nodes that I've gone ahead and created and loaded these 6 textures. I've also added multiply, add, and subtract. You'll find them by just using this term and searching here. So if we start with the first one, which would be multiply, I could go ahead and say that I grabbed from these 2 texture sources. I could go ahead and let's just move them to the side for the purpose of showing this. So if I go ahead, I multiply these 2, grab the color output, grabbing any of the red, green, blue would work fine as well, since this is black and white. Now this is what you would expect or can expect to get. And also worth mentioning, when you pull one of these out and load a texture, you won't see it like this per default. To get a preview of the contents or the result of that node, you hit this button. See that it's this one. Change into these 3 different modes. So no preview, small preview in this window, and a big preview. There's also, when I'm on the topic, there's this one as well, which allow you to expand and collapse the input and output functions. And if I do that, like that might be in the node editor, there's 3 different modes. In ShaderFX seems to be 2 different modes, either collapsed or expanded. Anyway, multiplying. So if we do the math here, you might already be aware of why we get this type of result, but just to clarify, if I say that I focus on this white area, this white area represents 1.0, and if this one is multiplied by the same area over here, which might be white as well, then I've got an equation which is 1.0 times 1.0, and 1 times 1 still equals 1. So this white area will be white here as well if it's multiplied by white on the other end, like in this case or this case. So the black areas, as mentioned, represent 0.0, and if I take 0.0 times whatever other value on this side, it's going to be black, regardless if this one is 0, 1, or 100. 0.0 times something is still going to be 0. So anything black here will for sure be black here as well. And that's true for this one as well. If I ask the question on this side, anything black here will for sure be black in the results. So multiply, as long as you stick to texture maps which are within the 0 to 1 range, as these are, multiply will only ever darken the resulting image. There's no points here that got brighter by doing this multiply operation. That only holds true, as just to reiterate, if these are in the range of 0 to 1, which a regular texture is. The only case I can think of where a texture isn't if you start using HDR textures. They would have a range which expand beyond 1.0. So let's try the same kind of thing if we mix it up with some of these ones, just to showcase. So these, as you can tell, they have the same kind of contents, but I've just shifted the colors around a bit. So let's say that I go for grabbing color here and I replace the black and white circle with the gray and white circle. I get this kind of result. So now I'm showing, just to clarify, these two multiply by each other. So still holding true, anything black will be completely black on this side. Anything where you have white times white will still be completely white. But the more interesting part here is this gray value here, which doesn't actually sit exactly in the middle at 0.5. It's likely 0.4 or whatever. If I grab that 0.4 and I multiply it, say down here, with 1, the equation will be 0.4 times 1 is still 0.4. So the same gray color is represented here. But where gray meets black, we still have the fact that I have 0.0 times something, gray in this case, is still going to be 0.0. So the two extremes, if you have white here, it's going to pass the same color as the second source has through here. And if you have black, it's going to make it black. So if this was a full color image, say a photograph, you could describe the multiply as where you have white, it's just going to pass through the photograph as unmodified. And where it has black, it's going to pass through black. And anything gray in between is just going to darken the photograph. So one last try. If I plug this one in here, you'll see I get this kind of result. White times white is still going to be white. White times a gray color is going to be that gray color. But a gray color times a gray color, and in this case they're both at around 0.4, is going to be 0.4 times 0.4, which is going to equate to something like 0.16, if my math is not incorrect. So that means that here, where gray meets gray, it's going to be this darker gray. Here I still have the 0.4 gray, and here's 1.0. Right, so that's the multiply node. Let's try playing around with the add operation as well to see what that does. So if I go ahead and just disconnect these, and I can move this one to the side. Let's start off with the same two that I started off with before. So if I take this one plus this one, and we look at the results, I get this type of result instead. So what's happening here is where white meets white, you actually have a calculation of 1.0 plus 1.0. So you're actually ending up with a value of 2.0 here. And where black meets white, you have 0.0 plus 1.0, which is 1.0. So within this circle, we have some areas which are 1.0 and with some which are 2.0. And the reason we can't distinguish between these is that 1.0 represents our whitest representation. We can't show off any color which is whiter than white. This holds true for black as well. You can get negative numbers, which you'll see when we get to the subtract. And you can't make the negative number more black than black. Although it's worth mentioning, this doesn't mean that the value is clamped or that you chop off the negative part or the part which exceeds 1.0. If you continue to manipulate this value, this is still going to retain or have those values which expand outside of the 0.1 range. It's only the visualization when showing on the screen which doesn't allow us any whiter than white or darker than black. So as mentioned, white plus white equals 2.0, black plus white equals 1.0, and black plus black each equals 0.0 or 0.0. So I think you're following with me on this so far. So let's just mix it up with a few other texture sources. So if I go ahead and do this, this is what I could expect. Still, white plus white is 2.0. The gray color, let's see, yeah, the gray color plus the black color is still going to be the gray color, since black is 0.0. It's basically any area here with a black is just going to look the same as the secondary source, or pass it through without no modification. Let's grab one of these, for instance. Let's grab this one, mix it up with this. I have this kind of result, which means, let's go through a few of them. White plus black, or 1.0 plus 0.0 is still going to be 1.0. The 0.4 plus 0.0 is still going to 0.4. The 0.4 plus 0.4 is going to be 0.8. So that's why I have both the brighter gray, the darker gray, and the white here as well. There's no black represented here, since I have black on this one, but since there's no black here, at least I'll have this amount. Even on this side, this equals 0.0, at least I'm going to, the total of the equation or the calculation is still going to end up with the results in here, which is 1.0 and 0.4. All right, so let's try the subtract node as well. So subtract node, start off with the same ones we did before. Share these two. Starting to feel a bit sluggish. I'm curious if it's due to the previews or let's push on. Right, so this is what we get when we try the subtract. So in this case, it's worth pointing out that both the multiply and the add operation doesn't really matter which input you put in which of these inputs here. So if you multiply this one by this one, or the other way around, this one by this one, or add, doesn't matter the order how you input these. With the subtract, however, it does make a bigger difference. So you need to really think it through. Is it this one I want to subtract with this one, or vice versa? If you just put numbers to it and you try to figure out an example, you'll realize that this holds true. So let's say 2 times 5 is still going to be 10, and 5 times 2 is also 10. 2 plus 5 is 7, or 5 plus 2 is also 7. But 5 minus 2 is 3, or 2 minus 5 is minus 3. So that does make a big difference. But let's just try walking this through and see what we get here. So we have on the left side of the equation, we have this area of 0.0 and 1.0. And when one of these white squares here meets the black area here, the equation will be 0.0 minus 1.0, since it's this order they're connected, which means that within this top square, this second square here, if you imagine this area here, you'll have minus 2 here, minus 1, and here you will have, let's see, we have 1 for this square, we have 1 here and 0.0 here, which means the equation is 1 minus 0, so you still have 1 over here. What else? Oh yeah, I almost forgot. Within this square area here, you actually have 2 areas, right? You have this one, which is sliced by the circle's shape, and on the left part you have the minus 1, and on this part you will have 1 minus 1, which equals 0. So you have both minus 1 on the left side here, and you have 0 here. Yep, so it's probably becoming quite clear to you now, but as the name suggests, the add operation will only ever make the result brighter. And this holds true as long as you have values between 0 to 1. So the add operation will only make the output brighter than the two inputs are individually. And the subtract will only make it darker. And same with multiply, will only make it darker. if it's within the 0 to 1 range. So let's try just a few other sources to see what this looks like. So let's try, for instance, I want to get this one. This. So top left square, we have 0.4 minus 0.0 is still 0.4. And this square here as well also has a little piece of the circle as well. So for this little piece here, you'll have 1.0 minus 0.0, so still the same white color. Then as we move on to the square here, you'll have both 0.4 here on the left side and 1.0 here. So 0.4, 1.0 minus 1.0 is going to be on the left side, is going to be 0.4 minus 1.0, which is minus 0.6. And for the white part or the right part, you'll have 1.0 minus 1.0, which is 0.0. So either way, it's going to be visualized as black, but you actually have minus 0.6 here and 0.0 here. So only making it darker. So that's it for just three of the most common type of math operators. You have additional math operations such as division, square root, power of, etc. So if we move on to the next point, which is what is a 3D vector. I'm not sure this qualifies specifically as math, but we're going to cover nodes in the future where you need to think of a 3D vector as a direction. So strictly speaking of data type, a vector can also be used to describe a value which has several parts, such as a float 2 or a float 3, for instance. However, quite commonly as well, when people talk about 3D graphics and shaders specifically, when they mention a vector, they might actually be trying to say a direction in 2D or 3D space. A common example of this is if you're familiar with the term of what a normal is, like a vertex normal, for instance. That value actually represents a direction of the vertex. You're probably aware, if you're familiar with the vertex normal, that as a vertex normal might shift direction, it's going to end up having the lighting on an object look as if it's received from different direction, the vertex normal is used to indicate what direction the surface has, which ultimately impacts such things as the lighting calculations. So what that 3D vector actually describes is a 3D direction. Now in the case of a normal map, you're probably most familiar with storing this value as colors, right? In Photoshop, you'll have the red, green, and blue channel. The red, green, and blue channel, as we mentioned at the start of this video, is actually a value between 0.0 and 1.0, right? Colors are represented as 0 to 1. So the red channel has 0 to 1, the green channel has 0 to 1, and the blue channel has 0 to 1. Now, these values, if you look at this 3D coordinate system, represents each of these axes. So for a normal map, for instance, the red channel represents the x-axis, the green channel represents the y-axis, and the blue channel the z-axis. Now if you take your values, let's say for our imaginary normal map, and I have a value along the red channel, which usually if there's no modification to the normal map, it'll sit at 0.5, right? But as your surface or the surface within the normal map changes direction, these values will vary. So you'll get one value along this axis, you'll get one value along this axis, and a third value here. And if you plot out these values and then draw a cube like they've done in this example image, then you draw from this orig or the center point here, and you drag to the opposite corner here, you'll have a 3D direction. So with these three values, you can use them to indicate the direction in 3D space. So in this case, you have values far greater than 0 to 1, which is fine. You can still indicate the same direction, the same exact direction by having values which are not as great. As long as the relationship between these, you might end up with a direction which only draws an arrow to this part, but it's still pointing towards the same direction. And that leads me into the second topic of vectors, and that is, besides actually just indicating a direction, as in this example, a vector has a length as well. So if you were to measure from here to this point, you'll get the length of the vector. That is also relevant for some usages. So I mentioned normal map being a common thing which you where you have a vector involved. Another thing is actually indicating light direction. If you imagine, say, a directional light, for instance, a directional light most definitely uses a vector like this one to indicate what direction is the light shining at. The interesting part is that the directional light in a real-time game engine will usually use the length of the vector as a means to store the intensity of the light. So a directional light which you have at a certain direction, as you're changing the intensity of that light in your 3D software or wherever you're working, you might actually internally be changing the length of the vector. So we can manage to both store the direction and a secondary, custom value, if you will, in this case for a light being intensity. So normal maps, lights, cameras as well. The direction, the user's camera, imagine your perspective viewport in Maya or whatever other 3D viewport or render. You have the camera as a vector as well as a direction. So why are these things important? Well, when we start creating shaders later on, we'll most definitely use normal maps. We'll want to calculate, say, the difference between a surface normal, that is the direction of a surface, a polygon object. For each pixel, if you have a curved surface, you'll have a different direction, and that direction is a vector. So we'll be comparing the surface vector, the direction, with the light's direction to calculate how much a surface is lit. Or you might compare the camera's vector with your surface normal to get more like a Fresnel effect, where you want to apply more or less of an effect as a surface is, grazing away from the camera, or like a phasing ratio component. So to reiterate, a vector, a 3D vector, is three different values. If you plot them in this coordinate system, you will get a direction, and that direction you can later use to do different lighting calculations or shader calculations. You can have a 2D vector as well. That's just using two of these components. If you imagine just the x and the y axis in a 2D space, you can use both those values to indicate the direction as well. So that's it for a 3D vector. A bit tech and abstract, I realize, but I still think it's something you need to be aware of because we'll be using it quite frequently. So I'll start blasting through my list of common nodes. So first on my list is something I wrote down as constants. Constants is probably a term you're more familiar with if you worked with, say, Unreal refers to these as constants. I'm not that aware that ShaderFX actually says constants somewhere on these values, but one type of constant, for instance, is a float value. So if I type float, you'll have the foremost common ones, or the only ones here, because the other ones are conversion nodes, are these, which is float, float2, float3, float4. So a float is a decimal value, a float2, and we can see this if we look in the attribute editor. Float is a decimal value, float2 is 2 decimal values, float3 is 3 decimal values, and float4 is 4 decimal values. So this one is usually something you use for, say, like an intensity of an effect, for instance. This one could be for manipulating UVs, where you have two components, U and V. This one could be for RGB, or maybe even for XYZ, or defining a 3D vector. And this one could be for RGB and an A component. Say you want to use it for transparency, or maybe if you're doing matrix calculations and you have a 4x4 matrix, you need 4 components. So these are some of the constants available. You'll have int, which is an integer as well, which is a whole value with no decimal part. So not that far from a float, but there's no decimal component. And you'll have stuff like strings as well, which is also a string value. Also a constant value. And think they're referred to constants because they stay constant throughout the shader. So if I embed one of these in my shader, or put one of these in my shader and I set 3.0, there's no dynamic part or updating part which is ever going to change this value. It's hard coded into the shader, so it's going to be constant throughout the process. And since we know it's going to be constant, we can actually optimize based on that. Or actually, that is probably handled for us by the compiler. We don't need to overthink that part, but it's constant because it's going to stay constant throughout the shader, as opposed to, say, a value which is feeding, I don't know, the light intensity or camera angle or something, which is going to vary and therefore always requires to be re-updated or recalculated. So we couldn't optimize on that part since we know that the value is going to be changing. So that's it for constants. Another common node is the texture map, which you've seen already. I used it for the examples for the color mat, but this is your texture map. Texture map, you click it and you can input my texture here. As I described in the first video, you can expose this one. You can expose the float as well in the previous constants I showed. You can input custom UVs. You can input specific bitmap level you want to use. And one thing I've not mentioned yet, but you can, when I say you can input UVs, that means it's not required. If it was required, you're going to have a red outline on this small circle here to indicate that it's required to work. And that is because if I go inside of this group, and just for clarity, I didn't show it in the video, but I'm in advanced mode, which I mentioned in the first video. Advanced mode, if this is enabled, allows me to go inside of this group. So if I go inside and I follow the UV input, you'll see that the UV input actually goes to a node called default value, and it's even labeled A if B empty, which means that the user can input something here if they want to, and if they do, it's just going to pass along whatever you put into this input. If you don't enter anything, it's going to default to this value, which means that it's not required for the user to input anything. It's fine if you just leave it as it is, and then it's just going to default to the first UV set. Same thing is true for the MIP levels. And there's actually no default value here, but this is going to act in the same manner. If you do input something, it's going to use your specific bitmap level. If you don't, it's just going to automatically use bitmaps in the way you would expect bitmaps to work based on distance. So you can input your texture. There's some optional inputs. From the texture, you can choose to read RGBA as a combined data stream as a float 4 value. You can grab just the RG and B component as a float 3 value, and then you can access the individual components RGBA as individual float values. Two other nodes which are very crucial, which you'll likely use in almost every shader you author if you continue with ShaderFX, are these. And I showed them in the previous video, but I just want to reiterate. These values will allow you to split up combined data streams and then construct together combined data streams. So just to show one example, if I grab a float 3, we can grab a float as well, for instance. I could input a float 3 here, and let's say that I'm just interested in grabbing the red component from RGB value here. I could just grab the X value and continue doing whatever my intention was with that value. Or if I needed to, if I come from a 3D space which is Y up and I needed to change to Z up, I could go ahead and swizzle these two values, just switch them around like this. Or I could, for instance, let's say I have an RGB value like this, and I want to add a custom A value, like an alpha value, the 4th channel. I could just pass on I could actually just skip this altogether in that case. I could grab from here and grab this one and, build together my own RGBA from an RGB source and an A source here. So vector component, vector construct, very important nodes that you should know about. We have two nodes called Saturate and Clamp, to mention them both. So Saturate and Clamp. So if you've touched on any of these type of shader authentic programs, or maybe some other type of technical interface where you work with nodes or these type of commands, you might be aware of the clamp command. The clamp command will allow you to take an input value, which might be a changing value. So at one point you might have one value, next second you'll have a different value, or etc. And you can set a min and max value. Say that you had light, sure, if we have a light intensity, for instance. Say that you had light intensity as an input value, and you didn't know what the light intensity was going to output. You might have a super strong light, and you wanted to handle the case where you made sure that you never went outside of a certain range. So to say that you wanted to have 0.0 as the min value because you don't want any negative values to pass through, and the greatest value you could have is 10. So on this end, you would now never have a value which is lower than 0.0 or greater than 10. How this works is if this value ever goes to the negative side, it'll just chop it off and convert any number below 0.0 to 0.0. Same holds true if the light intensity were to exceed 10. If I input 12 here, it's just going to chop off the 2 and leave me with 10. So it's not rescaling the value, it's actually just chopping off anything beyond max or below min. So that's the clamp operation. And if I have clamp between 0 to 1, that is exactly what the Saturate node does. It's very similar to clamp, but it's prefixed with being between 0 to 1. And this is quite a common thing. The range of 0.1 is I was about to say a sacred one, but a very commonly used range. You'll see it in a lot of cases. And if you want to just make sure that a value doesn't exceed the 0.0 to 1 range, it's actually more cheap and efficient to use a Saturate node. So in this case, where I have 0 and 1 in the min-max with a clamp node or a Saturate, this is the way to go in terms of performance. So this has nothing to do with a color in that sense. Most people, if they hear the word saturate, will think of like a HSV modifier, which can change the hue, saturation, or value. Or I think of it as the saturation component of a color. In terms of a shader, it's basically used to clamp a value between 0 to 1. The more efficient way of doing it rather than using a clamp. And on the topic of saturate and clamp, we have two nodes called min and max as well. So I'll need to grab a float as well. I should have just kept the float there. All right. So min and max are kind of like if you were to take a clamp and split it into having the min and the max part of a clamp, this is what you get with these. So they're used to set a minimum or a maximum value. Let's go ahead and paste 4 values just to show. So if we start with the min is going to take the smallest of the 2 values you feed into here and pass out as the result. So if I grab, just to showcase, and we can actually show this off with colors, since we have the color preview. If I do this, I have a value of 0.5 and I have a value of 1. If it's going to grab the smallest one of this is the 0.5, right? So I get that value. And this always messes with my mind, but you use a min operator to set a maximum value, and you use the max operator to set a minimum value. You really need to think about that, but what I'm essentially doing here is, let's say that I once again grab my light intensity, and let's say that I was only ever interested in setting a max value. I don't care about how small the value gets. I only care that it doesn't exceed 10, for instance. I could then plug this in here and set this value to be 10, and essentially now it'll compare these values and grab the smallest one. So if the light intensity were to go to 11 or 12, it's going to compare that to 10 and it's going to grab the smaller, so I get 10 here. So I've essentially now created a max feature to set the max value by using a min node. And same with the max operator, we can do the same kind of example there. If I grab another light intensity, and let's say that I want to make sure that the light intensity never goes to negative, can't go below 0.0. I plug this in, I plug this one in, I set this one to 0.0. So as the light intensity, say that it for some reason changes to -1, and if I compare -1 to 0.0 and I grab the largest of those two, I'm going to get 0.0. So I've now essentially created a minimum functionality here by using a max node. All right, so let's grab a lerp node. In ShaderFX, if you're familiar with the term lerp, you can't actually type lerp. Lerp is like a short for a feature actually called linear interpolate. In other, it's actually called lerp here as well, lerp operation, lerp op. In other software such as I think Unreal at least, and I think in other shaders as well, yes, you might be able to type lerp and it'll just find it for you. But here you need to make sure you actually type linear, or you could probably type interpolate as well. So what the lerp does is, that you can feed two input values, input A and B, or 1 and 2, and then you can mix between which one is going to get passed through based on a third value, which you use 0 to 1 range. So as an example, let's just grab two different color nodes so that I can set two contrasting colors. And I actually wanted to, sure, I probably deleted those textures I loaded before, but I want to grab one of those textures again. So let's say that I grab this one, for instance. So let's go ahead and choose two different contrasting colors. Let's go for red, which I didn't select for some reason. There we go. And blue. And let's feed this into the two value inputs. So I'll put this one here and I put this one here. And we can actually start off with the float value. Just to take it step by step, like so. So if I now show the preview here, you'll see that I have a blue color. And the reason I have a blue color is because my float value, which goes into the mix, is at 1.0. If I shift this down to 0, you'll see that it changes to the red color. If I leave it halfway in between, it'll be a mix of these two. So to reiterate, the lerp node will blend between the two input values based on a third value, and this value should be in the range between 0.0 and 1.0. This is what you get. And 0.0 is always the first value and 1.0 is the second value. So this gets even more interesting when I actually feed like a texture in here. So then I can get this type of result. Since essentially in this texture, a black color represents 0.0 and this 1.0. That would be similar as we showed with this one, but you'll have different values for different areas of the, the image or the rendered surface. Very useful node. It's actually, if you look it up, it's actually just a series of a few, I think it's like 2 multiplies and the add or something like that. But so you could reconstruct this just with math nodes, but it's far more easy just to use the lerp. But it's highly useful. So another node, which we'll probably use quite a lot, is the dot product. Dot product is used to, shouldn't be deleting this, I might move this. Probably not for the dot though, but dot is used to compare two different directions usually. So this is the node where you want to, compare, say your camera vector with your surface normal, or your light vector with your surface normal, or something like that, to compare, are these directions pointing in the same direction or in opposite direction or somewhere in between. So I can go ahead and show this on the polygon sphere. So let's just create a very small example for ourselves. So if I go for the, I think if I go for world normal and I find the vertex world normal, this is going to give me a surfaces normal. And if I then go for camera and vector, I will get the camera's vector. And you can get this as camera vector normalized. I'll mention what normalized is in just a bit, but for now I'll just pick the normalized value. And then I just because it's hard to showcase this in the small preview here, I actually want to just connect this to surface to showcase this. So I'll go ahead and plug this into the diffuse color, which it doesn't accept. Few other shader editors might automatically convert your float to a float 3, but in this case I'll have to do that myself. So vector construct, and I'll have to build my own float 3. So I'll just plug this into all three of the values. I will plug this into the diffuse color, and to avoid any confusion with seeing a specular highlight here, I'll go ahead and actually I'll go ahead and something like grab a float 3, and in the float 3 I'll plug that into specular color, and I want to make sure to leave this at black, which is essentially going to kill off the specular highlight. So now we can just focus on what results we get with this. Now if I have a look at my sphere, you'll see that it looks white and black, and regardless of how I rotate this, it's going to be black and white. And that is because I'm comparing, a surface direction. Let's go ahead and see if we can display one of those. So if I imagine that let's go to polygons, let's go ahead and show, say, the vertex normal. There you go. So I'm comparing these directions to the camera's view direction. So let's go ahead and just for showcasing, let's create a camera, like so. So if you imagine that camera having an arrow pointing this direction, or the direction of the camera is the view direction, it's going to compare the camera's view direction with that surface direction. So in the case here, and I actually think to be extra correct, I think Maya's camera vector is going to have a direction pointing in the opposite direction of how you view. So I think the direction is actually going to the right here. So when we compare that direction, which is going this way, and then a direction which is spot on, like directly in front of the camera, you'll have both the directions pointing in the same direction, or both the vectors pointing in the same direction. If you imagine this one being the inverted direction, like the arrow here, inverted of the direction. So when both of those 3D vectors are pointing in the same direction, you'll get an output of 1.0. And if you imagine this one with still this direction pointing straight down here, and if you compare it to a direction which is pointing straight out to the side here, for instance, you will get, and you put that into a dot operator, you will get a result of 0.0. And if I compare this camera's direction here with a direction going in the direct opposite vector going in the direct opposite direction, you're going to get minus 1.0. So the output of a dot operation is always going to be between minus 1 to positive 1. And just quickly, as the vectors are pointing in the same direction, you get a result of 1. As they're pointing with a 90-degree difference, you get 0.0. And if you have the complete opposite of each other, or a 180 difference, you get minus 1.0. And that actually explains why we always keep seeing white here straight on and black here, because currently I'm shading this sphere by comparing the surface direction with the camera's direction, that is the perspective camera, which I'm looking through. So it'll always be showing this type of result where it's white as a surface is pointing towards the camera and black as it's going away from the camera. And actually negative or minus 1 on the complete opposite end of the sphere. So dot operation, what you want to remember is comparing directions, and you get the result as minus 1 to 1. You have the length operator. So the length operator, as the name implies, is going to check the length, and you usually use this to check the length of a vector or a direction. So if I just open this one again, you can use the length operator to get the length this direction. So you do use it sometimes, maybe not that common, but I still wanted to put it here on the list since we were discussing dot. And it ties perfectly into the next part, which is the normalized node. The normalized node is going to take you usually use this together with a 2D or a 3D vector, and it's going to rescale a value so that the length of it is 1. Which means if I have a 3D vector, say float, or 3, sorry, and I have a value of 0.5, 2, and 3.0. If I were to plot in those values here, 0.5, 2, and then 3, I would end up with a direction, and the length of that direction is going to be far greater than the distance of 1. What the normalized then does is it rescales that value. So if you imagine you retain the same direction of that arrow, but it's going to scale down. So it's going to scale down until the length is exactly 1. And that is actually something you might not be aware, but like the data of a normal map should actually be normalized in order to calculate correctly. So if you were to edit a normal map, say in Photoshop, and you just go you know, crazy and paint with a brush without no sense of what you're actually changing about, or you modify normal with some exotic blending mode which you happen to like, you're actually shifting around these values. And as you're shifting them around, you're essentially changing the length of that direction the normal map is representing. And the normal map should ideally always have its vectors normalized to be in the range of 1. So for that reason, if you do ever change up a normal map, you want to make sure you normalize it afterwards to be absolutely correct, so you get the correct results. If you're using a software to bake your normal map, the result should always be, and as far as I know, would always be normalized. But as soon as you start changing it around and modifying a normal map, and if you're not absolutely sure what you're doing and make sure that you get a normalized results, you should essentially always normalize as the last thing you do when you're done with modifying your normal map. In other instances where you might see or come across the term normalize is, say, when you're accessing the camera vector. I'm not entirely sure what the non-normalized, what the length of the camera vector here represents. I'm not sure if it could be something like the far planes or some other type of extra data, but this one here is going to have the camera's direction, but it's going to probably have some type of variable length to that 3D vector, and the length represents some other type of attribute or property. Whereas the normalized, I can make sure that this one is always a length of 1. And the world normal would also be a length of 1, since that one is also normalized. So since I have both of these normalized, since both of these are 1 of length, I can then expect to get the type of values I just described with the dot operator. If you change up the length of these, if I grab the non-normalized one here, or if I had some custom length on my world normal, that would shift around the value, the results of the dot operation. So the reason to make sure that you have normalized values is if you're relying on things like the dot operator to always spit out these -1 to 1 in the fashion that you're familiar with, you want to make sure that you feed in normalized values. So I realize that this is going from quite basic math to quite techy subjects, but I just wanted to mention this. Once we start using these further on in future videos where we start using them, I'll recap on what the nodes are doing. So we just covered dot operator, the length operator, and the normalized operator. So next one I want to show is the pow, or power of operator. Pow. This is the same as taking one value, the x value, and raising it to the amount of y. So the way I usually think of using this one most of the time is if you're familiar with, say, Photoshop. I'll go ahead and start Photoshop actually. Photoshop, that load in the background. I've got an old CS6 version, but this should still be the same. If you're familiar with Photoshop and if you've ever used, say, like the curve tools, that is usually how I think of my power of feature. My license is not acting up. I do have a proper license, but either way, let's see if I have some Windows example in this. It's a shame. So bird, for instance, I thought I would be able to access, say, my. I'm just gonna grab whatever image here, like this one, for instance. I thought I would be able to just neatly grab one of the sample images from Windows. Obviously, those didn't exist on my computer for some reason. So here I have a nice image by Yoel Aid. It's not going to mind that I just on the fly grabbed one of his images. But if I go ahead and add a curves layer like this, if you're familiar with doing these type of operations, this is exactly the type of results you would get, or very similar, by using the power operator in Shader. You've probably done this at some point in when you did math at school or whatever. But if you're not using this on a regular basis, you might not be exactly sure what to expect with it. But thinking in terms of visuals on an image, a power of operator can be used to get this type of result. So if I want to get this type of result with a power operator, I would show you. So if I do this, and I can go ahead and see, do I still have one of my textures? Yes, sure, why not? Let's grab this one, and let's feed this one to color here. And then I'm not sure, but I'm think that the power operator will accept me plugging a float into the second component. If not, we'll have to construct. Yes, that works. Perfect. So if you use power and you input on this the y, this value, if you input 1, it's going to be completely unmodified. As soon as you raise this value to be above 1, it's oh, actually, it's a silly thing to be using a black white one here. I would need something with a grayscale value. So sure, let's grab this one. As soon as I raise the value to be above 1, it's going to darken the image. It's going to do similar to what this is actually doing. So in the power, when I raise the y to be above 1, it's going to gradually do this type of thing. And in this type of thing, if you're familiar with the curves, the black value is going to stay completely still, and the white value is going to stay completely still. And it's the values in between, all the grays and the light grays here, those are going to be the ones that get affected. So for that reason, in Maya here, we're not seeing any change on the dark color. We're only seeing a change on the dark gray here becoming even more dark gray as I raise the value. I can continue raising this value, and it will gradually get darker and darker. I mean, you might not be able to tell with just by eyeballing this, but now that I raised it to the power of 3, the dark gray areas here are probably not 0.0, but they're very close to 0.0. They're becoming very small at this point. And similar, if you wanted to do this kind of thing to brighten the image in this fashion, you would, with the power node, you would take this value and make it smaller than 1. So as I'm gradually doing this, you would see, I have to let go of this every time to show, you would see that these dark gray areas are going to be get brighter and brighter. And that is the same. If I had this pick one dark gray area here, and I just kept tracking that what was happening as I did this, you would see that it gets gradually brighter. So to reiterate, on an unmodified image, as you lower the y part of the POW to a value lower than 1, you're essentially doing this. And as you raise it to something higher than 1, you're essentially doing this. All right, so I'll leave it at that. POW can be really useful. There's Frack Node, which I want to mention. Frack, if you're familiar with modulus node, you can use Frack to usually get the same type of result if you're using the modulus to set it just to 1 or to loop at 1. But what this essentially is doing is, if I'm plugging this in here, it will take the decimal component of the value and just output the decimal component. So if I had a value of 2.3 going in here, it'll strip away the 2 and just give me 0.3 here. And if I input 3.3, I will still get 0.3 here. So the result would still be the same here if I compare 2.3 and 3.3. Why would this be useful? The way I usually or most often use it is if I have the time node, for instance. If I'm making some kind of interesting animated shader effect, I can do this, which will give me some useful results, because time in Maya will just keep increasing. And if you're going to be using time in Maya, remember that you need the time slider and to actually hit playback for this one to update. So assuming that I'm hitting playback, this value will just keep increasing. I think it represents with a second. So each second with your setting in Maya will output 1, 2, 3, 4, etc. But it won't just be integer values. It will gradually grow. So you will get integer parts and decimal parts here as well. But the interesting thing here is if you imagine this one just growing as a graph, the graph would just keep climbing like this. But if I input it into the fractional operation, the results would be 0 to 1 and then drop down to 0 and 0 to 1 and drop down to 0. So more like a sawtooth kind of effect. So if I wanted to loop something between 0 to 1, this one would always give me value 0 to 1. And to be extra exact, it would give me values between 0 to 1, 0, 0.0 to 0.99999. It actually never hits 1, I think. It shouldn't. So, but you could essentially say that you get values between 0.0 to 1, but actually you never specifically hit 1. So that is the Frack node. Let's go for the seal node, which is for sealing. And I'll just take the floor node as well, since I'm showing seal. These kind of go hand in hand, or are the exact opposites of each other. So if I input a value of still using the 3.3, a sealing value will take the input value and push it up to the closest integer upwards. So a 3.3 would equate to a 4.0, because if I take this and I round it upwards to the closest whole number, the closest integer, I would get 4. Floor does the opposite. It'll push the value down to the closest integer, so rounding it down. So 3.3 with the floor would give me 3.0. So those are quite simple. It's nothing more fancy than that. The invert 1 minus, you could essentially do this with just a subtract node and an extra float value, but it'll save you just one node and makes it more obvious what's going on. But this one is very useful when you're working in the range of 0 to 1. You use this one to actually invert a number, if you will, on this scale. So you could imagine it as inverting around the 0.5 value. So if I input 0.3, this is actually going to do the math operation of take 1 minus whatever you input. So 1 minus 0.3 is going to give me 0.7 out here. So you'll see that this one represents a color of 0.3. This one will represent the color of 0.7. If I just flip that around, if I do 0.7, I get 0.3 here. So the equation would then be, or the calculation would be 1 minus 0.7, which will result in 0.3. So essentially, and if I input 1, it's going to say 1 minus 1 is going to be black. So it's essentially inverting or flipping around the 0.5 value, which is the exact middle gray. So dark color will be the opposite if you flip it around 0.5 in the bright scale. So that one is can be very useful as well if you want to just flip a value around. Another useful one to know about is the UV set. UV set is the node that you want to use just to access UV sets in Maya. I think you can, I might be wrong here, you'll have to try it out, and we'll probably use it in some of the shaders we'll do in this video series. But the UV set index value would likely equate to which UV set in an indexed order. So I think if you were to go to, let's see, UV, and I go to the set editor. If I had a polygon object and it had multiple UV sets, I would assume or guess that this is going to be my index UV index 0, index 1, index 2, index 3. If not, you should be able to use the UV set name and refer to the UV set by its name. In this case, map1 or UV set or UV set 1 or UV set 2. And the way you do that is, if you drag from this one, you'll see that it's expecting a string, and it's actually expecting the one called string value. You'll know that because there's a v here as well. So string value is the type of data you're looking for. String and value. And I think these are hidden if you're not in the advanced mode. So make sure that you're in the advanced mode to be able to access them. So string value, I can then plug that in here, and I should be able to write map1 here, for instance, or what was the other names? UV set 2, for instance, to grab the last one. So on this one, I would go in the value here and type UV set 2. And then I would expect to get those UVs here. So that is the UV node. There's a normal map node. And the normal map node is very similar to the texture read node. So like probably delete texture. Let's create a texture map also just to put them side by side. So this is essentially a texture map node with some additional functionality inside of it. You can still input a custom UV input. The normal height, I think, is just a scale factor to change the intensity of your normal map, if you will. And those are the two inputs you have. I would assume that you can still grab these two inside of here, but they're not exposed by default. You get the normal value out, and you can also get the alpha component. And on a technical note, if you look inside of this one, I think the main difference on this one is that it's actually transforming. So I think all of this is identical to the texture map node, except this one where it's converting your tangent space normal into a world space normal, if I'm not mistaken. Yes, seems like that. Takes the world normal here. Space normal. Yep. All right. So your normal map. So you would use that for cases like where it says normal in here is where it's expecting to get your normal map. You have a reflection cube map. If I just type cube map, you'll see that there's both reflection and refraction. You'll likely be using the reflection most often. And that one is just used to, if you want to add a cube map for reflections and ambient lighting, you would use this one. This one is also a variant of the texture map node, but also adds some additional functionality. So you might need to specify, depending on what you're doing. If you're using a normal map, you need to make sure that normal map goes in here as well. And that's likely the only thing you would need to input, depending on what you're using it for. You can then go ahead and input this one into the reflection here, for instance. As with both the texture and normal map and reflection, you specify the texture path here, and you can expose them. And if you look inside of the reflection cube map, it's adding additional nodes for things like the reflection vector. And of course, the different sampler nodes and whatnot are set up to be saying that it's expecting a texture cube and not a texture 2D. You have a Vertex Color Node. Type Vertex Color. Let's see, I always keep confusing. There's two of them. I think there's two if you're in advanced mode, and otherwise you'll just find one of them. But if you're in advanced mode, which I usually am, I will sometimes get confused which one I need, and then I usually just end up putting both of these out here. But this is the one we want, like so. So this one is, as the name implies, it's used for accessing vertex colors in Maya. So similar to how I just showed the UV map, you can either based, I think, then on index, which is the index order in the list of vertex color sets, or the vertex color set name, which is one I usually use this one just to make sure that I get it right. You can refer to the vertex color set. So if I in Maya were to add a Vertex Color Set. So if I go to Color Set Editor and I hit New, and I want it to be so, I could then refer to this Vertex Color Set just by typing Color Set as it's phrased here with the humpback style. So same thing here, this one is expecting a string value. So string value, then I would need to type color set. Now I would get the vertex colors here, just as say your texture, where you can choose either the RGBA, RGB, or the separate parts. We've got Vertex World Normal. Actually ended up showing that earlier when I showed you the dot operation, this one. But if I go here and I go inputs common Vertex World Normal, this one will give me the normal direction of the object, that is these normals. This is not the normal of your normal map. If you're using the normal map node, this node is actually a part of the normal map. Then you get both this value modified by the normal. But if you want to grab just the geometry normals, this is the one you want to use. So it's useful for things like comparing the camera vector to the world normal, for instance, or the object normal. You have vertex world position. This one will give you the position of the vertices, and each sampled pixel, not just the vertices, even in between here, you'll get the positional value for that pixel. And that can be useful for things like, say that you want to start playing around with doing vertex shader. You want to have an animated geometry, for instance. Then this one will give you, the initial position of your object. And then you could go ahead and modify that position and then feed the modified results into the object vertex position here. So if I went ahead, I'll just do, it'll probably be quite boring, but it'll just be a proof of concept. I'll show you how we can just offset the object using a vertex shader feature, which will just add a user-driven value. So if I now try playing around with this value, you'll see that I'm actually now offsetting the position of this sphere. So it's adding this number I feed into both the X, Y, and Z part of the position of this one. So that's by just grabbing the initial position of the object and just adding a value to both X, Y, and Z in this case. So to reiterate, this was the vertex world position value. And the last two I had on my list, I've already shown both of them, I think, or at least one of them. But one is light vector. There you go. And the other one is camera vector. And I've definitely shown and spoke about the camera vector. I used it here in the dot operation. But this one is going to give me the camera's aiming direction, either as a camera vector without the normalized length and a normalized vector. And the light vector is essentially doing the same thing but for lights. So if I had a directional light, for instance, I could choose to either get it non-normalized, that is, the intensity of the light represents the length of the vector, or normalized. And for this one to work, you can see that you can actually indicate which of the lights you want to use by using the light index. And that is similar to the UV set and the vertex color. This is a int, and it's int value, you can see by the V. So I would need to use the int value if I want it to be specific. I think it works even though you don't input, but if you have several lights and you want to choose one of them, you need to indicate which light by using an index value. So now I could grab the direction of the light. Yeah, that should be it for light vector and camera vector. I think that actually concludes my seemingly, at least when I planned it, my short list of notes, but it ended up taking a while going through all of them. I hope you found it useful, and if not, you could refer back to this video at a later point if you've forgotten what one of these notes do. Hopefully some of this will stick, and as I mentioned, later as we're doing shaders, I'll reiterate a few of these explanations for these nodes, especially the more complicated ones. So that's it. Thanks.